This next section we're going to talk about is going to be direct variation and proportions. So we've actually worked with this a little bit before, but now we're going to add more solid terminology to it. So we've worked with fractions quite a bit. When we're talking about some kind of equation involving two fractions equal to each other, that's what we call a proportion. So a proportion is a statement that two fractions are equal. So to show you what I mean, let's look through an example. Suppose you make $15 for 1 hour of work. If you then want to figure out how much you would make in 2 hours of work, you go ahead and just multiply the 15 times 2. So you would make $30. Okay. So we can actually write this using a proportion to show you it's the same thing. So we can say $15 over 1 hour of work is exactly the same as $30 over 2 hours of work, because they boil down to the same numbers. If you ignore the units, 15 divided by 1 is exactly the same as 15 divided by 2, or 30 divided by 2. And in reality, you can rearrange this a ton of different ways as long as you're consistent. So if you notice in this particular example, I put the money in the top and then we put the hours in the bottom. And I just stayed consistent in the pairing. The 15 and the 1 hour went together and the 30 and the 2 hour went together. So a second way I could write this is instead I could set up two fractions and I'll put the hours on top. So I can say 1 hour divided by $15 is the same as 2 hours divided by 30. Okay. So if you plug these both into your calculator, you would see they're exactly the same fractions. Or really, to get from here to here, you're just multiplying top and bottom by 2. And really, I have even more proportions that I could write from this. Okay. So instead of putting the pairs and keeping hours and dollars together, I can go ahead and do the 30 divided by the 15. Okay. All I want to do now is stay consistent in my pairing. So in the numerator of this one, I want to put the hours that go with the $30. And so that would be 2 hours over here. And then the hours that pair with the $15 is 1. And so if you look, 15 or 30 divided by 15 is 2. 2 divided by 1 is also 2. So the units really don't matter here. You can set these up however you want as long as you're consistent in your pairings. So we're going to utilize these to set up some kind of equations. And a lot of times we're going to have to solve for one of the unknown components. So in this first one, we're going to solve this proportion. And we have this unknown amount x in the top. And so the easiest way, we don't like the fractions, to get rid of them, we're going to go ahead and use that technique of cross multiplying. So we're going to go ahead and do 25 times 7.5, and then the 2 times the x. And if you go ahead and multiply the left-hand side out, this will give you 187.5, and then 2x on the right. So to solve for our unknown x, we go ahead and divide both sides by 2 to make these cancel. And then 187.5 divided by 2 gives us 93.75 as our unknown x. Okay. So proportions tend to pop a lot up when you're talking about runners, when you're talking about working, when you're talking about like items, scaling them up and scaling them down in the quantity, size, and the price. These appear very frequently. So we'll look at a runner for this next problem. We're told that Sam runs 6 miles in 50 minutes. If he's keeping that same pace, we're going to figure out how many miles he would run in 35 minutes. Okay? So you could find his pace if you want, but we really can just set up a proportion for this. So I'm going to go ahead and set up my two fractions. We've got one equaling another. And I think it's easier. We know the pace is 6 miles in 50 minutes. So I'm going to put that in one fraction. 6 miles for every 50 minutes. Okay. So when I go to do the right-hand side, I want to stay consistent, put miles in the top, minutes in the bottom. We have no idea how many miles he runs, but we want the time to be 35 minutes. So to solve for our unknown, we'll go ahead and cross multiply to just get rid of these nasty fractions. And we've got 6 times 35 and 50 times x. So I'm going to ignore the units for now because it would just make things really messy. So we know in the end that my unit should be miles. So if you do 6 times 35, that's going to give us 210 is equal to 50x. And then one last step to solve for x, we go ahead and divide by 50. And that will make these two cancel out. So if you do 210 and divide it by 50, we're going to get 4.2 is equal to x. So our distance that he would run is 4.2 miles. Okay. And this makes sense because if you think we're decreasing the amount of time that he's running, we should decrease the miles because he's keeping the same pace. So really another formula that you can use for this, if you're trying to find the distance someone's going to run, it's equal to the rate multiplied by the time. So if you think of you're driving 60 miles per hour for 3 hours, you multiply the two to figure out how far you drove. Okay. So this is a really great example of something that's going to be known as this direct variation. So here, if the number of minutes decreases that Sam runs, what happens to the number of miles? And then what happens if we bump up the number of minutes, assuming that he can keep this pace? So if he runs less time, he should run less miles. If he runs for more time, he should run for more miles. Okay. So this kind of particular relationship is important for us because what's happening to one quantity is exactly happening to the other. But there is one extra stipulation for here that I'm going to add into this. If he runs for no time, he runs for no miles. And that might seem silly to point out because, yeah, you're not moving, you're not running at all. There's no way that you could run any miles. But this is a really important stipulation. If you have none of one quantity, we need to have none of the other. So in this particular relationship, we say that one quantity varies directly with the other. Or we can also say that these two quantities are directly proportional. So to kind of figure out, just based on a bunch of different problems, if we talk about something having this direct variation, what will it look like in terms of an equation? What will that look like graphically, numerically? And then if I just hear this inside of a phrase or inside of a problem, how do I know that I'm in this type of relationship? So what you're going to see verbally is you're going to hear the quantity y varies directly as the quantity x. And now the key is there's going to be some number that's relating these two. So in this last example, that rate was a fixed amount. he was keeping that same pace. So the time and the distance varied directly. As time went up, the distance went up. As time goes down, the distance goes down. So there's going to be some constant in all of these problems that relate the two quantities. So this is known as the constant of variation. And it's denoted by a K. Okay. So to show you algebraically, what you're going to see is the quantity y varies directly with x. So it's going to be some constant times x. This will be a fixed number, or just a constant. So to give you an example that we're going to use for the numerically and graphically, you might see that y is equal to 3 times x. Okay, so some number times x. So I'm going to set up now using the same equation what we're going to see if we have a chart going on. What kind of patterns can we see? So in the case when x is equal to 0, my y component is 3 times that. So my y component is also going to be 0. If x is equal to 1, then my y will be 3 times 1, which is 3. If x is 2, my y is 3 times 2, or 6. For 3, my y value would be 9. And when x is 4, my y is 12. So really what you have each time is this value of y is going up by 3. And that's exactly that linear relationship. You can see here, it's really just a linear equation. Y equals mx plus b. Just happens to be that we're going to have a y-intercept of 0. Okay. The other way we can kind of recognize this is what happens to one quantity is going to happen to the other. So if I look from here to here, when my input is doubling, meaning being multiplied by 2, the same thing happens to the output. The y value gets multiplied by 2. To go from 1 to 4, you multiply by 4. So the exact same thing should happen to this y value, and it does. So if I'm given a chart, this is going to be how I can figure out if I've got direct variation. Just going up by a constant isn't enough because it has this particular point where it needs to go through 0, 0. Okay. So graphically, I'm going to graph again this same exact line. My first point is 0, 0, and this is the important one. It must go through the origin. So it has to be through the point 0, 0. If it does not, it is not direct variation. It can still be a linear relationship, but not direct variation. Okay. And then plotting a couple other points. When x is 1, my y is 3. When x is 2, my y is 6. So connecting our dots gives us this line, which is 3x. Okay. So again, super, super, super important. It has to go through the origin. So let's try this example first before we then work with some set equations and charts. We're told the ratio of men to women working for a company is 7 to 5. If there are 192 employees total, we want to figure out how many women work for the company. Now this is a little bit of a hard one. So I'm going to show you how to set this up in 2 different ways, and you'll still end up with exactly the same answer. So the first one is probably going to be the approach that you want to go through, and it's actually a little bit of a harder one. So I'm going to set up a proportion because they give us a ratio of men to women, and remember, ratio is going to indicate a fraction. So the ratio of men to women is 7 to 5. So this is representing the number of men in the top because it's men to women. Okay. which means then on this side, I should also stay consistent, men to women. The problem is I have no idea how many men or women there are, okay? But my goal is to figure out how many women work for the company, so I'm going to make that my variable. So I'm going to say W is the number of women in the company. Okay. The problem is I can't put this 192 in the top. This is telling me the total number of employees, okay? So instead, if I know there are X women, to figure out the number of men, I'm going to subtract the number of women from how many people are in the company. So to break this down into simpler terms, say I were to have 2 women, that would then force 192 minus 2, or 190 men to be in the company. So really, I need to use an expression up here instead. So this is going to be the total number of people minus the number of women to give us how many men are in the company. So it gives us 192 minus W in the top. And this is why, although this seems like the really natural approach because you have that 7 to 5, you have to break this down by the number of men and number of women. So going through to solve for this, we need to go ahead and cross multiply. So that will give us 7 times W and 5 times 192 minus W. I've got to multiply the whole thing out. So we need to go through and we need to distribute this 5. So this gives us 7W. And this is where I'm going to take some liberty of not writing everything out. You have to do 5 times 192. That will give us 960. And then 5 times W gives us 5W. Okay. Now I want to solve for W, so I've got to isolate that. And it makes sense that I've got 2 on both sides and this constant over here. So I'm just going to go ahead and I'm going to move that 5W to the other side. So we go ahead and add 5W. So this gives us, this gives us 12W is equal to 960. Okay. And then one last step to solve for W, we go ahead and divide by 12. And this gives us W is equal to 80. So there are 80 women in the company. So this is probably the natural approach to set up this problem because of the way this ratio is given to us. But what I want to do is show you a different way, because instead I'd rather find the ratio of women to total number of people in the company. Okay. So we've got this ratio of 7 to 5. And this is the number of men to women. I can then change this to go from women to the total in the company. So I'll call it C, right? So there are 5 women to every, and now I'm going to add these 2 together to get the total number in the company. So it's the number of men plus the number of women. So really, I can change this ratio to 5 to 12 to get the total number of women to the company. So, and I spelled ratio wrong up here. I'm not an English person. So the ratio of women to the company is going to be 5 to 12. So this just makes it a little bit easier and cleaner that I don't have these nasty expressions. So instead, I can set up my proportions as women in the top and then company in the bottom. And we're going to do the same thing on both sides. So our ratio is 5 to 12. The number of women is unknown, but the total number in the company is 192. So to solve for this, we go ahead and cross multiply, and that gives us 5 times 192 is equal to 12W. 5 times 192 is 960, is 12W, and you see we end up with exactly the same equation. So when I go ahead and divide by 12, I still end up with W equaling 80. So not as intuitive to go through this approach to start, but it's definitely a little bit easier of an equation to solve. So completely up to you. Okay. For this next one, we want to determine whether X and Y are directly proportional. If so, we want to find that constant of proportionality. So what that means, because it's directly proportional, do I have the form y equals a constant times x? So starting with this first one, although it's backwards, yes, indeed, this is some constant times x. So I have exactly the same format for directly proportional. So this is a yes. It forms a nice line. If I plug in x equals 0, my y value is also equal to 0. So this is a yes, and my constant of proportionality is -5/8, whatever's attached to x. Okay. For b, if you look at this, it has the form y equals mx plus b, so it is a line. However, it is not that form a constant times x. So I've got this +7 at the end. This means it's not directly proportional. Or we don't have a case of direct variation. Okay? If this was gone, then I would be sitting pretty. But because it's there, it does not go through that origin point. If you plug in x equals 0, your y value is equal to 8 times 0 plus 7, which leads us to 7. So it doesn't go through 0, 0. Because if I have no x's, I should have no y's, and unfortunately, that's not the case here. For this next one, we're going to be given a bunch of tables. We're going to determine whether it shows direct variation, and then we want to write the equation for the direct variation when it exists. So looking at this first one, you can kind of tell it's a linear relationship because it's going up by the same amount each time. But again, that doesn't guarantee that we have a direct variation situation. And the problem is because I don't have when x is 0 what y equals, I can't use that technique. So instead, what I need to do for this is I need to see if I do something to the input, does the exact same thing happen to the output? So looking from here, if I go ahead and double this input, meaning I multiply by 2, the same exact thing happens to the output. And likewise, to go from 5 to 15, you're tripling or timesing it by 3. The same thing happens to the output. So because exactly the same thing is going on, this is a case of direct variation. So what I want to do is I want to come up with the equation for this, okay? So that immediately tells me that I know it has the form that y is equal to some constant times x. The problem is I don't know what this constant is. So I'm going to utilize the chart to help me out. When x is equal to 5, my y should equal 8. So we're going to use this to find the value of k. Plugging in that y is 8 and x is 5, we just need to divide both sides to find the constant k, because that will make these two disappear, and we have our unknown. The value of k is 8/5. Okay? So our equation is the y value is equal to 8/5 times x. And you could then go back, and if you plug in 10 in for x, you should see that your y value is going to be 16. Likewise, if you plug in 15 for x, you should see your y value is 24. So you can verify that you do have the correct one. Okay. Now moving on to the second one, if you look again, it's going up by the same amount each time here, but that doesn't guarantee that I have direct variation. So I want to see what's going on a deeper scale. So if I look to go from 3 to 6, that means I'm doubling the input. But if I look at the y values, 5 times 2 does not give me the end result of 6. So this is not times 2. I really don't know what's happening here. And because of that, immediately I know this is not direct variation. So what happened to the input did not happen to the output. So I don't have that particular scenario going on. Okay. So the last thing we want to talk about with this is when we're dealing with these direct variations and proportions, it's really actually going to pop up the most when we're dealing with shapes. So if you think of things in your everyday life, a circle is the same shape across the board. You're just scaling it up or scaling it down. So you have bigger circles or smaller circles depending on the objects that you're working with, but it's the underlying same shape. Same thing with a lot of triangles. You take one triangle and you can multiply all the sides by something to get a bigger one, and it hasn't changed that base structure. So this is a particular phenomena that we like to call, we have a couple different things, but we say these shapes are similar to each other when they have that same underlying base structure. So if we take a figure and we scale it up or down by a factor, what we're really doing is we're taking each side and we're either multiplying or dividing it by the same quantity. And what that does is it results in a very similar shape, which is scaled sides. So we say these shapes are similar to each other. Okay. If it happens to be that when you multiply or divide by this number, nothing changes and every side has stayed the same, then we say the shapes are congruent. Okay. So this thing that we're multiplying or dividing by is called our scale factor. It's how big we're making it, or how big we're blowing up each side by, or what we're dividing by each time. And I don't really pay too much attention to the scale factor because it's always going to depend on your starting shape, what it actually is. And we'll look through an example like this. Okay. So the only thing that's being affected here is going to be the side lengths. Every side is going to change by the same multiplying factor. So as a result of doing this, the angles in your shape are going to stay exactly the same. Just the sides are changing. So I'm going to look at an example here where we've got this rectangle ABCD. And so it's a rectangle, so the sides across from each other should be exactly the same. So these two sides are 10, the other two sides are 4. Okay. What I'm going to do is I'm going to use a scale factor of 1/2 to get my smaller rectangle. So what we tend to do is we put these little, they're called prime marks at the top here to indicate this side A prime corresponds to A, B prime corresponds to B, and then you can continue in that exact same pattern. So you kind of know the overall shape here. So all of the corners are still rectangles. They are exactly 90-degree angles, because it is a rectangle. So nothing has changed except our sides, okay? So I'm going to show you with a scale factor of 1/2. So what I'm going to do to get this side here is I'm going to take the corresponding side and I'm going to multiply it by that scale factor of 1/2. So I take the side length and I times it by 1/2, which is the same as dividing it by 2. So this side is going to be 5. And then likewise, to get side B prime C prime, I look at its corresponding side, and I'm going to go ahead and multiply that by 1/2 to get that this side is going to have length 2. And then I really don't need to do any work for these ones because they are the same. If I take 10 and multiply it by 1/2 again, this side is 5. And then for the last side, this side is 4. So when you multiply it by 1/2, this side is also going to be 2. Okay. The really nice thing about this is you can set up a ton of different proportions, and in the end, they'll all be the scale factor or they'll be the flip of it. Because again, if I went from here to here, what you've really done is take each side and multiply by 2. So the scale factor in that case would be 2, which is why I don't pay big attention to what the scale factor actually is. Okay. But the really nice thing is when I take any type of proportion that I can set up, you can see it's going to be exactly the same. So to show you, if I take side AB and I divide it by its corresponding side, A prime, B prime, that will be 10 divided by 5, which is 2. Okay. But now if I take side BC and divide it by its corresponding side in the new shape, that's 4 divided by 2, gives me the same amount. And really, no matter what pairs I look at, you're gonna end up with the same thing. So if I take side AB, BC, CD, or AD, and I divide it by the corresponding side, you're always going to get this quantity, 2. Okay. So in this case, it will always be 2. Or likewise, I could put these in the top. I could take A prime over B prime and divide it by AB. In that case, this would be 5 divided by 10, which gives me 1/2. Okay. Move this actually over here. Or if I take side B prime C prime and divide it by side BC, that will give you 2 over 4, which is still 1/2. Okay. So in the exact same manner, I could really flip all of these and still get a similar result. So this is something that's super beneficial because I can always set up a proportion involving 4 of my sides of these triangles to then solve for one of the unknown sides. Okay? And we'll do an example like that very soon, but let's just get some practice. We're going to determine if the shapes are similar or also if they are congruent or neither. So I'm going to zoom in for these just to make it a little bit cleaner. We're going to start with this first one. If I go ahead and look at this first triangle, these have side lengths 1 and 1, and this side length here is 1 and 4. So the problem is to go from here to here, we multiply this side by 4, but the same thing does not happen. So in this case, because not all side lengths are scaled, this means it's not similar. And because these two are not exactly the same, they are not congruent. So this is the case, it has neither. Okay. So congruent means you have exactly the same shape. Similar, yes, they are both triangles, but I didn't do the same thing to both sides, which means these angles here did not stay exactly the same. Okay. Trying the next one for B, we've got two circles here, and circles are super nice because they're always going to be similar to each other. But if you kind of break this down, remember this has a radius, which is our important quantity. This radius is 3, so the distance from the center out to any edge is 3. And likewise here, the distance out from the center to any edge is 1. So yes, these are similar because they have a same base shape of a circle. There's no other way you can draw a circle without it being exactly the same, just a scaled up version. However, because these have different radiuses or radii, they are not congruent. Okay. Moving on to this shape, I've got to go ahead and see what these side lengths are. So for this one, it's 4, and for this side, it's 6. And then looking at the smaller one, this side is 3, and this side is 2. So although it doesn't quite look like it, we can actually pair these so that they are similar shapes. So to get from side 3 to side 6, we go ahead and multiply by 2. And then to get from the side 2 to 4, we're multiplying that side by 2. So these ones are going to be similar. I've multiplied both side lengths by something. It's just happened to be that they're rotated. But because they are not exactly the same, they are not congruent. Okay. Let's try one more of these. So if I look at these two shapes, really these side lengths are exactly the same. So this side is 4, 2, 1, 1, 3, 1. Same thing, 4, 2, 1, 1, 3, 1. Absolutely nothing has been done to any of these. They are exactly the same shape, just rotated. So that means indeed they are congruent for sure because they're the same shape. And really, although it's kind of tricky, that means that they're similar to each other. So it's kind of like congruent is that special extra case because your scale factor is just 1. You've taken each side and multiplied it by 1 to get the other. So if they're congruent, they're automatically going to be similar to each other. Okay. So I got one last example. We want to find the length x of this triangle. And although we're not getting really deep in geometry, what you can pretty much assume in these cases is that you are going to have similar shapes within here. The problem is right now how this looks, it's not so clear cut. So what I'm going to do is I'm actually going to break this into 2 different shapes. I'm going to cut along here and work with 2 separate triangles. Okay. So I've got this one triangle with that right angle, which did not turn out nice. Let's see if this will work better. This side is 3 and this side is 4. Obviously things are not drawn to scale. That's okay. And then I've got this other triangle here that just happens to be upside down. Okay. So just to kind of give you an idea of why these are similar, you see they both have this right angle in here. It happens to be that these two are exactly the same. and these two angles are the same, because in reality, they both form a straight line. So this is something that's called vertical angles, which forces them to be the same. And since 2 of 3 angles are the same, the third one is going to have to be the same too. So if you're moving on to a different class, or if you remember from geometry way back in high school, these two are called vertical angles, which means they are the same to each other. Okay. So that's our smaller triangle. Now what I'm going to do is I'm going to take this one and I'm going to rotate it. Good enough. Okay. And then I got to be careful with my placement. Across from the 90-degree angle should be the side X. Okay. And then if this is this angle right up here, it should be at the very top when I rotate it. And so X and the 4.5 form that angle, which means the 4.5 is the value right here. Okay. So I've got these two similar triangles now, and I want to solve for this unknown. So 3 pairs with the side 4.5, and then 4 pairs with X, because those are the sides across from the 90 degrees. So I can set up a proportion because I know that the ratios of these are equivalent to each other. And I can take the same triangle on one side. I could do the same in the tops. Remember, you have a ton of ways that you can set up proportions. So to make things simpler though, I know the 4 and the X pair together. So I'll go ahead and say 4 divided by X, since those are the like ones. And since 4 went in the top, I'm going to pair 3 in the top of this other one to stay consistent. And then the side corresponding to it is 4.5. So to solve for our unknown side X, we go ahead and cross multiply. So if you do 4 times 4.5, it should equal 3 times X. 4 times 4.5 is 18, and that's equal to 3X. And then I've got one last step to solve for X. We go ahead and divide by 3. So our value of X is going to be 6. Okay. So if it's pretty obvious what that scale factor is, you definitely don't need to set up a proportion, but I have no idea what I multiply 3 by to get 4.5. So I don't really know what I have to multiply 4 by. But if it was a little bit more clear cut, like say this was 6, to get from here to here, we would multiply by 2, which means you would do the same thing over here. So you don't always have to set up a proportion. It's really just a matter of how obvious is that scale factor going to be.